with that. So what's the direction of it? N. So it's n dot r in direction n. Okay. Right, so we've got this expression here. We're now going to use the idea of a quadratic form. I don't think that you've come across these. So it doesn't matter. We're just going to pull some black magic out of the hat and then see where it goes from there. So what I'm going to do is I'm going to write these dot products as though they were products of two vectors. The product of two vectors, when you have to take a dot product, like product of two vectors, what do? You take a row vector and multiply it by a column vector. Correct? So, I mean, if I want A, B, C, dot, D, E, F, I could also just write it as A, B, C times D, E, F. Row vector times column vector will give me the same answer. AD plus BE plus CF. So, instead of writing n dot r, I can write n transpose r. So let me try that and see what happens. So this expression here for r per squared is equal to, well, let's leave this guy. This is just a scalar. It's uninteresting. Minus, this guy is also a scalar. It's got structure to it. So let's consider what happens if we take it as n. I'm going to underline the n because I'm thinking of it as a vector in a column space. So I transpose it and times it by r. And that's squared, and I may as well just times it by itself. N transpose r. Now, n transpose r and r transpose n are the same thing. I'm just putting one vector in front of the other vector in front of it. It doesn't make a difference, right? I mean, A, B, C times D, E, F is the same thing as D, E, F times A, B, C. If you compare these, this one is A, plus B, E, plus C, F, and this one is A, B, plus B, E, plus C, F. So they're the same. Because these guys here, A, B, and whatever, they live in a commutative world. So, in other words, they're real. So these things are the same. These things are the same.
Is n still a unit vector?
N is still a unit vector. It's just, I'm not putting a hat on it because I'm thinking of it as a column vector. But I mean, it's a unit vector. We know that, so we don't have to put the hat as long as we are confident it's a yes. Right, so the point is I can write this in any order. So let me rewrite this guy in an order that is convenient. In particular, I'm just going to swap these two guys around. So it's going to now look like n transpose r transpose n. Okay, all I did was the last two, I swapped them. And I can swap them because it will make no difference to the answer. But vectors and matrices, they are associative. I can group these however I like. So nothing stops me from grouping these middle guys together and making a matrix. And when I do that, what do I get? I get r squared minus n transpose r transpose. Well, we can write that out. What is r? R is simply x, y, and z. R is simply my position vector. And r transpose is simply the transpose of that, x, y, and z. Times by n. Can I multiply those two matrices? Sure I can. Those two matrices can be multiplied. So let me do it. R squared minus n transpose. This gets x squared in the first term. What's it going to be? This is a 3 by 1 and this is a 1 by 3. So the product will be 3 by 3. So there's x squared here. And then the next term will be x, y. The next term will be x, z. And down one will get y, x. one final step. This term here is becoming annoying because it doesn't look like this one. I want everything to look like n transpose times the matrix times n. So this term just looks like a number. So what I would like you to remember here is that n transpose times n is equal to unit vector person 1. Correct. N is a unit vector, so n transpose times n is 1. And I can multiply anything by 1. So I can multiply r squared by 1. I can multiply it by n transpose n. So I can write this whole thing as n transpose n times by r squared, but I choose to put the r squared with an identity matrix. Now, it's going to be confusing to put I for identity when we've got I for moment of inertia. So instead of putting I for identity, I'm going to put an underlined 1. And this is the general notation. Instead of putting I for identity, we put an underlined 1. Because we've got I for moment of inertia. Right. Times n. And we subtract this. I'm not going to write this out again. Minus n transpose times some matrix. Right. So now we can write everything out as n transpose times something times n. So it's n transpose times r squared times the identity matrix minus that matrix there times n. And let's compute what this is. What's this matrix in the middle here? Well, the matrix in the middle here looks like r squared times the identity. What's r squared? X squared plus y squared plus z squared. So this matrix here looks like x squared plus y squared plus z squared, 0, 0, 0, x squared plus y squared plus z squared, 0, 0, 0, x squared plus y squared plus z squared, minus this matrix here, x squared, xy, xz, yx, y squared, yz, zx, zy, z squared. And when we subtract those, what do we get? Well, the difference is simply y squared plus z squared minus xy minus xz minus yx x squared plus z squared minus yz minus zx minus zy and x squared plus y squared. Right. So that's the difference between these two matrices. We multiply it by n transpose and by n. And that's what we get as an answer now for r third squared. Final answer. Final answers are lovely things. And then let's get everything we can before. This is what we call a quadratic form. It's a matrix multiplied on two sides by a vector to get a single number. And that number is going to be quadratic in the elements of n, in the elements of the normal vector for our axis. Alright, so let's see why this is nice. Why do we bother doing this? Let's find out what the moment of inertia is going to be like then. The moment of inertia is now given by a simple expression. Remember that I above my axis n is simply given by the integral of r term around that axis squared dm. Now I have an expression for r term around that axis. So I know what to integrate. I integrate everything there. But now n is not going to be something inside my integral. I can take my integral inside that matrix, right? Because I'm only going to integrate over the region. The region is independent of the axis around which I'm rotating. If I'm rotating a cube around some axis, the region defining the cube is independent of the axis. It's still a cube, no matter how I change my axis. So my integration region is obviously independent of n. That means I can take my integral inside that matrix. So what do I get? I get n transpose times now the integral of these guys. Integral of y squared plus z squared dm. Integral minus integral of xy dm. Minus integral of xz dm. Minus integral of yx dm. Integral of x squared plus z squared dm. Minus integral of yz dm. Minus integral of zx dm. Minus integral of zy dm. Integral of x squared plus y squared dm times 6. So now you should see that n sits on the outside, these integrals sit on the inside, and they're things we can compute. And we can compute them for our object. And once we've computed them, we've got this matrix. And once we've got this matrix, we can get the moment of inertia around any axis. We simply put the axis here and here, turn the handle, and out comes the moment of inertia around the axis. So this matrix, we call it the moment of inertia tensor. It's a tensor because it has two indices, the matrix. Right? Tensors in general, we're not going to get into them now. I'll just tell you that a tensor of order 1 has one index, a tensor of order 2 has two indices, a tensor of order 3 has three indices, like a matrix that is actually a cube, and so on and so forth. And there are different ways of combining things and different ways of making them interact with each other depending on whether they're covariant or contravariant. We don't care. For the purposes of this course, we call this guy inertia tensor. But in our hearts, we still think of it as a matrix. So the inertia tensor is a very general object, and it is completely characterized by the object that we are studying. I'm going to take questions now before I move on, because then I'm going to work this thing out for a cube to give you an example of an application. But I first want to take any questions. Is there anybody who's a little confused about what's going on here, why we're doing this? No. Anyway. Yeah. Right, so whatever axis we have, we pre-compute this quantity for our object. Let's say it's a black water. So I choose x, y, and z on the black water. Then we put the black water. Right? And then I compute these quantities. All of them. Over the black water. Now I have a tensor, a matrix here, that has numbers inside it. Now you choose an axis around which to rotate this stuff, no matter what your axis is. And you'll get an answer here. If your axis changes with time, you should make your axis change with time. You'll get a time-dependent answer. Right. Yes, question.
Why must your axis be unit vector?
Mine must go with the unit vector.
Yeah.
Alright, the axis doesn't have to be a unit vector. And then all that would happen is when we were doing this, we divide it through by the norm of the matrix of the axis squared. And then all over the show we have dividing by the size of the axis squared. And eventually here we have divide by the size of the axis, divide by the size of the axis. So when we got to the end, we say, oh, we need to use a unit vector. So you don't have to use it in derivation, but when you get to the end, you'll find that if you didn't use unit vector, you get divide by the size, divide by the size. In which case, use unit vector. Does that kind of answer your question? Right. So I think at this stage, we've got the machinery, this guy called the Inertia Tensor, to do just about everything. But there are still a few niggling things, actually implementing it, and so on and so forth. Now, in the notes, I've done it for a cube, and I've done it for a cone. And then I've further gone on with the cone case to solve for the Lagrangian of a general cone-shaped spinning top. Spinning top people right now are thinking, yeah. So, I'm not going to do all that here on the board. It's a lot of tedious stuff, and particularly when you're going to do it on Mathematica. In the notes, I've given Mathematica statements that will generate this whole thing for you in one shot. 3 lines. Very nice. I'll ask you things about this moment of inertia tensor, sure. Maybe not so much in the test as in the exam. 1 or 2 small questions in the test. But there are other things about it that we have to look at. The first thing is this. Can you tell me anything about this matrix? Is there any property that shines out at you like an oasis in a desert?
Symmetric.
Yeah, hearing that mumble, then good. Symmetric. The matrix is symmetric. xy is equal to yx, xz is equal to zx, zy is equal to yz. In fact, we generally write it like this. N transpose, and we call this thing here ixx. We call this one ixy. We call this one ixz. We call this one iyy, iyz, and izz. Right, and now the others are just mirrors of them. This is still ixy, this is still ixz, this is still iyz. So it is a symmetric matrix. What about the entries? What can you tell about the entries of the matrix? These are squares. So these are squares. So the square of a real number is always negative. And so these entries are all non-negative. And in fact, positive if the object is not squashed. So every single entry, well, these ones are negative, these ones are strictly negative. Or are they? These are squares. The diagonal entries are strictly positive. The entries are not zero. And they are all real numbers. The matrix is real and symmetric. Algebra techniques. Diagonalization. You guys done it yet? Yes. Diagonalization. Yes. So, when a matrix is real and symmetric, what does it mean? When a matrix is real and symmetric,
That you can always diagonalize it.
yes, you can diagonalize it, and even stronger statement, you can diagonalize it by means of an orthogonal transformation. So, I'm not going to prove this, and I may ask it to you to show in an oral test, not in a test, to show that the eigenvalues of this matrix are real, and to show that the eigenvectors associated with different eigenvalues are orthogonal. And that matrix of eigenvectors, if you know how to diagonalize a matrix, that's the thing that diagonalizes your matrix. Now that's an orthogonal matrix, because those eigenvectors themselves are orthogonal. So we can diagonalize this with an orthogonal matrix. What does that mean? It means that the eigenvectors, if we think of them as new directions, those eigenvectors specify new directions in which this matrix is diagonal. Cutting all of that extra information out, I'm going to state for you what that means. It means that no matter what your object, whether it is a cube rotated around its endpoint, whether it is a cone rotated around its center of mass, whether it's this TV rotated around my arm, it doesn't matter. Whatever your object, whatever the point about which you're rotating it is, and that's a point, not axis, because this guy defines the point. Whatever the case may be, this thing can be diagonalized by choosing the eigenvectors at that point. We call the eigenvectors, those directions, principal axes. If, and this is the most important thing, if you didn't follow any of the math, it's fine, as long as you catch this final point. If we choose the right orthogonal coordinate system, the right Cartesian axis for our object, that matrix will always be diagonal. Okay, the spectral theorem, all these things, real symmetric matrix, help us to claim that there always exists a choice of axes for any object for which that matrix is diagonal. How do you find it? You generally look for symmetries. For a cone, you generally think, well, one of the axes must point along the central axis. If you cannot find it by intuition, that's okay. You choose an arbitrary Cartesian axis. And then you get something that's not diagonal. So what do? You diagonalize it. The eigenvectors will tell you, in terms of what axis you have, the axis that gives you diagonal moment of inertia. That's quite a bit to swallow. Remember, Wednesday and Thursday, tutorials and questions. Check chapter 3 notes, make sure you understand them, make sure you're confident with them, and if you're not, Wednesday and Thursday is a good time to come and bring up your grievances. So that's what's called the principal axis. There exists a Cartesian coordinate axis for every object along which the moment of inertia tensor is diagonal. Those axes are called principal axes. And then your moment of inertia tensor looks like this. I1, I2, I3. These are called principal components of the moment of inertia tensor. Rightio. The kinetic energy. Remember we said the kinetic energy could be expressed in terms of the moment of inertia? And indeed it was. You can go through the steps of derivations. I'll just use the book in chapter 3 for the steps of derivation. It turns out that if you replace these ends with your angular momentum vectors, then you're computing the kinetic energy. Right? Angular momentum vector, angular velocity vector, remember that's just a vector that points along the axis of rotation, and its magnitude gives you your angular velocity around that axis. Right? So it's easy to show that this is the case. I don't feel like going through more derivations because I think that's just going to touch up things. But derivations are always known. This is like very short. Yeah. Right, so the point is that omega here is an angular velocity vector that points in the direction of the axis of rotation, which is not a unit vector. In fact, its length is proportional to how fast you rotate. Yes, we have been computing it as a unit vector, but we've been computing something else, right? Not t. And t, remember, looks like a half I in the right direction omega squared. That omega squared can multiply one here to change the side of our vector. It does work, but I don't want to complicate. I don't want to complicate the vector by deriving it. If you want me to derive it, you can. Okay. Right, so the point is we can get the kinetic energy in a very simple way in terms of this tensor, or in this matrix. But once we know the principal components of the matrix, if we are clever and we get right, or we go through diagonalization, we know the principal components, t becomes even simpler. And thus, if you get anything out of the entire matrix, you should get this next formula that I write down. energy. Yes. Well, we've got a formula for it. Omega transpose. And I can write it in this form. I1, I2, I3, omega. It's simply equal to, when we write this all out, well, half. I should have put a half up there. Right, there's a half over there. So this thing looks like this. A half times I1 omega 1 squared plus I2 omega 2 squared plus I3 omega 3 squared. What this says is the following. If we've identified our principal axis, our angular velocity vector has components, omega 1, omega 2, and omega 3, in each of those directions. It's a vector. Every vector can be written with components in any direction. In particular, we can write with components in the directions of the principal axis. When we do that, we write out the expression for the kinetic energy and we get this. It's much simpler than multiplying matrices in general. We simply have this one expression. Right, I think that is quite enough information to absorb. It's quite a bit there. I encourage you to check out chapter 3's notes. They are comprehensive, particularly the last bit on the momentum of the inertia tensor. I've also included a section in the notes that I haven't mentioned here because I believe I will overload you with information. It's something called Euler angle. Your pitch, yaw, and roll. It details how to relate Euler angles and principal axes on a rigid body. I'm not going to talk about it now. I really think it's confusing. But read it. Read it and come on Wednesday with questions. Right. We have 10 more minutes. What I'm going to do in those 10 minutes is I'm going to compute this thing here for a cube. And then we'll start. Right. When I say I'm going to complete this thing here for a cube, I mean a cube rotates around one of its vertices. So the cube is rotated, you can think of it as taking a cube in a cube. There we go, we've got a cube, and we simply move it around this vertice. And we ask the question, what is the moment inertia tensor when we do that? And we ask the question! What is our moment inertia tensor when we do this? I'm going to continue speaking at this pitch. Because it's fun. And because you are annoying. Now, the moment of inertia tensor is going to be each of these components, which we're going to compute around the cube.